Okay, so my name is David Henty. I'm do a lot of training and education at EPCC, in particular training on the MSc. And a while back, I did a workshop at RSECon 3 years ago, I think, and it seemed like a good idea to kind of rerun it. And I will just show you where we are. So hopefully, is that coming through? Yeah. So this was the oops, this is where the course material is. I'll put the URL in the chat. So it's the original course, or it was a half-day workshop. It's called "Make Your Python Code 10,000 Times Faster with Parallel NumPy." So I've given you the URL there. That material is there. Some of it may not be 100% up to date. Some of the particular instructions may be specific to what we did on that day, but the general concepts are all fine. But what I was going to do is really just go. I think, I haven't given this talk for a while. I'll go over it quite briefly again, just to give you a feeling for what techniques you can use in Python to improve your performance. And the two really key ones are NumPy, which we'll see improves the performance of numerical codes by significant amounts, but also to do parallel programming at large scale, you can use MPI like you can in C and Fortran in MPI, but that also requires you, assumes really that you're using NumPy. So they're linked together. I should say that the reason I developed this workshop was to force me to learn more about Python. I hope I know quite a lot about parallel computing, high performance computing, and MPI programming. I know very, very little about Python. So if I'd be very interested if any things I say are not particularly correct, or I infer the wrong things, then the programs are there just to demonstrate things. They are my way of writing Python, which is basically C translated into Python. So the first thing I'll do is give a little overview of the application we're going to do. So we're going to take a real application, or something that approximates a real application, and we will work through it and hopefully see it going faster. So this exercise, this model comes from my message passing programming course that some of you may have been on. And it's a thought exercise, and I'll just go through the start of it. So the major observation is that we want to predict traffic flow. We want to have models that allow you to predict how traffic moves, because it's quite an important thing to be able to do. Because what you want to do is you want to avoid things like this. You want to avoid congestion. This is a video of Bangkok, I think, how the traffic builds up there. So you want to do that. Now, in reality, you use very complicated computer models. This is a computer model that was actually run on by EPCC back in the early 90s. This is around about near Edinburgh. But we're going to do something incredibly simple. So what we're going to do is we're going to have an incredibly simple cellular automaton. And I'm going to show you a Python program that implements this. We're going to try and make it go faster. So you may be familiar with cellular automata from things like the Game of Life. Conway's Game of Life, we have a 2D grid of cells, which are alive or dead, and you have a deterministic update rule. We're going to do the same thing, but we're going to do about the most simple thing you can imagine. We're going to divide the road into a series of cells, and the cells are either going to be occupied or unoccupied. And for reasons I may come back to, these are drawn as police cars. And we have one and only one. So we update the cellular automaton in a set of steps. And there's only one rule, is that each step, if a car can move forward, it does, and if it can't, it doesn't. And it's an instantaneous update. So what we say is, that car can move, that one can't, and that car can move. Okay, we don't move to it, so we label them, then we move them, and then they move. So we perform a number of steps. Each step car moves forward if space ahead is empty. And so we go to that situation here. Now that car can't move, that one can, and that one can, and then we get this situation. And then when you get car gap, they move off quite happily. And I'll not go through this in any more detail, other than to show you that it is a ridiculously simple model. It does have its own Wikipedia page if you're interested. I think it's rule. there's a particular yeah, I think it's no, it's not 182. I'll come back. There's a Wikipedia page on this, which I'll come back to. And the analogy I used in the course was doing this by moving pawns on a chessboard, but I really just want to show you that one more slide. This may be a ridiculously simple model, but it does predict relatively reasonable behavior. It gets traffic lights right. So you have some traffic lights, cars are lined up at the traffic lights, and they don't move off in a block. They move off one by one. So as the lights go green, the cars move away, spreading out, and you may not even get past the lights. But the other thing we're going to do is what you can do is you can look at congestion, and what you can measure is the average speed against the density of cars. Now, the density of cars is the percentage of cells that are full. So here we have 1, 2, 3, 4, 5, 6, 7, 8 cells, 4 cars. So the percentage density is 50%. And the average speed is the number of cars that move divided by the number of cars. So if the average speed is 1, it meant that every car moved. If the average speed is 0, it meant that none moved. And if you run the model, you find, not surprisingly, that at 100% filling, no cars move. And at 50% filling, they eventually move at speed 1 because they arrange themselves car gap, car gap, car back, car gap. And so at 50% or less, I've lost my cursor, 50% or less filling, you get you asymptotically get unit velocity. Everybody moves, but what is actually quite surprising is how quickly congestion sets on. It's relatively interesting, but it is an incredibly simple model. But what we're gonna do is we're gonna write a program to solve that. Okay, so what we're going to do is I'll show you the repo page where I have a very, very simple piece of code. It's simple because it's a simple algorithm. Is also simple because I said my Python is not particularly good. Whoops. So if we go to here, so what I will do is I'll quickly go through this, but I'll set it running to start with. It takes a long time to run. So let's run this model. So this is just a Jupyter notebook. That was my other reason for for running the course, was to find out about Jupyter notebooks. So what happens here is we basically have three roads, we have a number n cell, which is how many cells we have, which is set to 1,240,000. Is that right? No, 10 million. It's 10 million here, and we have a road containing all those cells. The temp road is just for setup, but the new road and the old road, we have to have a new road and an old road because it's not an instantaneous. It is an instantaneous update. So you have to create new road as a function of old and swap back. We initialize them with a certain density, so that's temp road. Now you'll notice that these cells are bigger. These roads are bigger than they need to be. They're actually for n cell cars. They're n cell +2, and that's because we want to implement periodic boundary conditions. What we want to do, we're actually going to simulate traffic on a roundabout. When a car moves off the end, it reappears on the start. So if I think of the cells being numbered 0 to n-1, the neighbor up the way of n-1 is not n, it's 0, and the neighbor down the way from 0 is not -1, it's n-1. And the important point about the cellular automaton model, why it's surprisingly analogous to real programs, is that at each iteration you update the state of a cell, of an array element, based on its value and its nearest neighbors. And that is exactly analogous to what you do if you write a program which is based on simulating partial differential equations. When you discretize those equations on a computer, you end up with update schemes where the value of a cell at the new time step is dependent on its value and its neighbors. Now, the update will be more complicated for fluid dynamics or something, but the structure is the same. And we implement periodic boundary conditions by having these ghost cells, and I'll explain that later on. So to get started, maybe I can make this a bit bigger. That might help a bit. Yeah. So to get started, we have this temp road is just to initialize them. And we initialize it randomly. We'll come back to that. And what we do is we loop over a lot of iterations. We update the boundary conditions, and what that means is we copy the value of cell 0 into cell n, and the value of cell n-1 into cell. Sorry, we copy the value of cell 1 into cell n, and the value of cell n minus 1 into cell 0. So that means when we look upwards from cell n minus 1, we get cell n, which has been set to be the value of cell 0. So it's just a trick for implementing periodic boundary conditions. Why it's important is this is just a trick in the serial code. You could implement it other ways, but in the parallel code, it turns out to be the best way to do parallelism. So I just basically loop over a lot of iterations. I update the boundary conditions and I update the road, and then I copy back new to old. And all this is done in completely naive Python with Python lists and Python for loops for all the updates. And if we look to the top, the functions I'm calling are the initialization one is just it just initializes the cars randomly. It picks a random number and it sets the road based on the density. So we have a density close to a half. So about half of the cars are filled. The update road is the important thing. Basically, we loop over the road and we say, okay, we loop over all the cells. If I'm currently occupied, if the guy in front of me is occupied, I stay occupied. Else I move and I become 0. Else, if I'm unoccupied, if the cell down from me is occupied, it moves into me, otherwise I still 0. So this corresponds to a car not moving from an occupied cell. This corresponds to a car moving from an occupied cell. This corresponds to a car moving into an unoccupied cell, and this corresponds to unoccupied cell staying unoccupied. So those are the rules. We'll come back to it. You can re-express this like this, and I'll come back to that. That's the way which is going to improve the performance. And the update boundary conditions is just this thing where you implement periodic boundary conditions by explicit copying. So that all looks fine. And if I've run the program, it's taken, to do 100 iterations for this road, it took 0.9 seconds. It took, what's that, 4 minutes. And I'm quoting the performance in megacops. Now, a real program, you quoted performance in megaflops, floating point operations per second. Megacops is car operations per second. So there you go. So that turned out to be very, very slow. So the first thing we're going to do is recognize that Python operating on arrays with Python loops is unbelievably spectacularly, incredibly slow. So if we look at the better one, you'll see here that there is also a traffic numpy. And if you look at this, the main program is almost the same, except the arrays are declared as numpy arrays. So we have this np.zeros. Now, I'm declaring the array to be integers. You might say, why aren't you declaring them to be characters? Because they're just cast, they just could be zeros or ones. It's because I want this to be, I have a C program which does the same thing, and the C program uses 32-bit integers. That's what I'm doing here. And it does exactly the same thing, same functions with a slightly different concept, but we're using numpy. So the two things about numpy are A, you declare the arrays in a different way with this numpy syntax, but B, you can operate on whole arrays at a time. So here's a very simple one. If I want to copy the old road to the new road, I don't have an explicit loop. I do old road of 1 to n cell plus new road of 1 to n cell plus 1. And that, now remember, my array indexing goes from 1 to n cell because the 0 and the n plus 1 are these ghost halo cells. But basically that's what NumPy allows you to do. It replicates what was invented in Fortran in the early 90s, Fortran array syntax, and it replicates it in Python. You can arrays become first-class objects. You can do operations on whole arrays, and that makes things incredibly quicker. So, for example, that's just a simple copy. But if you look at the actual update loop, this is the update road. It looks a lot nicer. I basically say, now I have to do two things with the update. I have to do a copy, but I also have to do an if. So you'll see that in the loop, in a Python normal loop, there's an if. The whole point about NumPy is you want to do entire operations on arrays. Apply this stencil, this operation to the whole array. And the way you do an if in NumPy, surprisingly exactly how you do it in Fortran, is where. So this says for the whole array where the old road is naught. So and you can do so this is, instead of doing loops, you have array indexes. So for if the array for every element for the array, if for every element of the array, if the array of 1 is 0, then old road, yes, sorry, it says where this is equal to 0, okay, then this is this is set to this. Sorry, so long ago I wrote this that I can't quite parse this, but basically this is saying that where the road is 0, it's equal to what's going down the way, else it's equal to sorry, what's going up the way, else what's down the way. But this is the equivalent of that if statement written in array syntax. So the important point in Python NumPy is you have to basically express things in array operations. So for example, we can't count the number of moves as we go through the array. We have to do a single thing. So what we say is, well, we count the number of elements where the new road is not equal to the old road, and there's a sum operation. So things like wheres, which are the array equivalent of ifs, and there'll be sum operations which add up lots of rows. This I have to divide by 2 here because this actually double counts. It counts a car moving in or a car moving out, which is double counting. But the important point is that you have to express all your operations in single expressions on whole arrays. And I think the one that illustrates it most easily is the simple copy. Copy all the elements of this into that. Okay. Now, if we run this, so we've got about, you'll see this should get the same answer as before. So what do we get before? Before we should get 0.898941, and it ran at 4 megacops. And this is the same answer, but it's 90. So you're already 50 times. I'm going to write these down. You're 4 goes to 200. Okay. So we're already 50 times faster. So that's pretty good, and we'll see later on how that relates to the performance of something like a C program. But what we're going to do next is we're going to do message passing. Now, I'm kind of assuming here that you know about MPI and message passing to do this, but I'm showing you how you implement message passing in Python. And the way you do that is there is also a private. No, it's not there. Sorry, it's traffic MPI. So you'll see that here the init road and the update road are effectively the same, okay? However, what we do is we do a message passing decomposition of this. So what we say is, if we had a road of length 100 and 2 processes, each processor would get half the road, okay? So what we see now is we import, now the interface from Python to MPI is via a module called MPI for Pi. All it does is a wrapper that allows Python, so you still have your MPI library, which is a C library, but you have this wrapper which allows MPI to call the C library. And as well as that, it exposes a slightly nicer interface to MPI than the raw C one. Okay? And so, for example, if you're familiar with MPI, you would normally have a function call called MPI com size. In MPI for Pi, the communicators are the objects, and the MPI functions are methods on those objects. Yeah, apologies if my terminology is not quite right, not being a real Python programmer. This again is basically copied from the now deprecated C++ interface. So MPI used to have a C++ interface which had this structure. The communicators were the objects, and your methods and your functions were methods on those objects. That was discontinued in MPI for technical reasons, but it's a useful way of doing it. So this is all very, very, very similar. The important point is that what this says is I'm an MPI program, how many processes are running on, and this will be a number if I'm running on 4 processes, 0, 1, 2, 3, and the rank is who am I? And the most important line is here, okay, n local. My arrays are now n cell over size. I'm doing the same simulation of 10,240,000 cells, but each process only has an array of a smaller array, a much smaller array. And so I check that this is all, and then all this code is basically the same, except it's n local instead of n. So I still have a large array. Big road is still the full size because I want the initialization to be consistent. So there's a bit of technicality there, but the main point is that all your new road and your old road are n local plus 2, not n plus 2. They're smaller. Now the init road is the same. Now to make the code consistent, I initialize the road in serial. It's very hard to get reproducible random numbers in parallel, so I'm reproducing serial, and I then have this function called scatter. This says scatter the big road I've initialized here to all the other processes. Again, this is the standard MPI function, but wrapped up in a Python syntax. The other thing which isn't obvious here, but all MPI routines in Python and MPI for Pi have two versions. One is a capital S, which operates on NumPy arrays, and that is fast, okay? Because a NumPy array is just a C array. It's just a pointer to memory, okay? Good old-fashioned programming. But if you want to send a Python object, you have to do a lowercase s, and that will I'm going to get the terminology wrong, but that will serialize pickle. Is it pickling in Python? It will be unbelievably slow. Okay, so although you can call MPI for Pi on any list or Python object, they're designed to be used on NumPy arrays because scientific and technical programs which MPI is used for are designed for NumPy arrays. I have to compute my neighbors because it turns out now, although I can update most of my road, I can't update the values at the end because the values at the end depend on the values owned by my neighboring process. So I have to say, well, who's the guy up from me? Well, if I'm rank 3, he's 4, and if I'm down, if I'm rank 3, my neighbor down the way might be rank 2. But I have to have cyclic boundaries because remember, we've got this roundabout. So just have a bit of bookkeeping here. But basically, this code here is very, very similar. Okay. We do a update road and we do a copy back, but we have to do two things which are slightly different. One is we have to now in the serial code, the boundary condition is just a copy. I implemented periodic boundaries by doing a copy. In the parallel program, that requires message passing. You need to talk to your neighbor. And we have the send receive operation, which basically says that I want to send my extreme element to my neighbor up the way and receive my boundary element from my neighbor down the way, and then do the opposite thing. I want to send my extreme element to the lowest element down the way, and I want to receive from the other guy up the way. And so that is almost the only MPI needed in this code, and that is the MPI equivalent of on the serial program doing this copy to complete the circle of the periodic boundaries. I then update the road, but the other thing you have to note is each process will get a different answer here. This is how many cars moved on my section of road, but I want to know how many cars moved in total, and so I do an all reduce, which is another standard MPI function. And for some reason, I copied it in and out here. So it's really quite simple. And if you look at the instruction, you can actually run this on your laptop. So I can now in Windows, you have to do something slightly weird. There we go. But you'll see we get the right answer. 0.8941. That was the correct answer. And it took about, it was very slightly, about 200 megacops. Okay, that's fine. So but that's just running on one. So this is saying run this program on one process. And so there's just a bit of overhead to do with some of the Python bits and some of the MPI bits and pieces. What I really like to do is, does it go fast on two processes? Let's have a look if it does. So we're looking for 0.898941 and 227 megacops. What do we get on two processes? A bit faster, okay, not even 50% faster, but it did go faster and we got the right answer. Now, the reason it's not doing very well is my laptop has only got a few CPU cores and it's running all kinds of nonsense, including this half a dozen Python notebooks. So it's never going to go particularly fast here. So I use the notebooks for these parts, but I really wanted to use ARCHER2. So we, so if you, I'm just checking out the right window here. So it's a request. I have slightly difficult for me to track my questions here. I see I have a question. So what do you mean by the duplicate? So if you if you look the URL here, which I posted, I'll repost in the chat, is a GitHub repo. You've posted that in. So you put, yeah. It's best to ask questions in the main chat into everyone. That's why I got confused. Sorry. So if you, it's best if you could you post questions in the main chat. That came as a private chat. That is the the URL, and in there you will see that there are where are they? They're in notebooks here. There's lots of Python notebooks lying around in here. Does that answer the question? They should all be there. So what I'm going to do now is to actually go on to Cirrus, and I will have to just, I've done something slightly silly here. I'm going to have to basically I'm not Cirrus. I want to share my. So I have quite a few windows to manage here, and I'm not doing a particularly good job. So hopefully you can see me here. So I'm now just logged on to ARCHER2. If you have an ARCHER2 account, you can do the same. Yeah. So let's get the repo, and that's just the repo brought over. So now. Okay, so let's first of all go into the, I called it Python HPC. Let's go to the code. Now, we're not running through a notebook, we're just running raw code here. There's lots of stuff here, but basically, I would just go to, I have the Python serial code here. Now, on ARCHER2, you have to load a module called module load cray Python. And I will, just to make it quicker, I will reduce the number of iterations. This is just because, remember, it took about 4 or 5 minutes to run. I can't really wait that long. So I will run for fewer iterations. I'll reduce the number. So if you run for a reasonable number of amount of time, the time that the megacops is car operations per second. That should be constant. Okay, it doesn't matter how many iterations you do; it's doing a time per iteration. There are some startup, but so this will probably be slower than my laptop because ARCHER2 is an old beast, and you know, has been running for many years. The processors in ARCHER2 are relatively slow. There are 750,000 of them, more than my laptop, but the individual processors aren't particularly exciting. But we will see that if we run that, so we've got about 4.4 megacops on my laptop through a notebook. Here we got about 5. Okay, maybe the Cray Python's better. That is slightly fake because this is on the login node, and for various reasons, the login nodes can be faster than the compute nodes. So I should, to be, this is some magic. Basically, I will run this on the compute nodes. The reason that the compute nodes are, the login nodes are faster than the compute nodes is the login nodes are general purpose nodes which do a frequency boost. If they see somebody running a program and there's not much going on, they'll boost the frequency. Whereas the compute nodes, assuming you're running big parallel jobs, need to keep the power consumption low, so they are fixed frequency. So I would expect this to be slightly slower. And this is just running exactly the same program using the Cray Python on the nodes. And I would expect it to be a bit slower. So let's write this down. It is, you can see it's a bit slower as well. So this is the very, very, very naive Python. and we were getting more like 3 megacops. Okay. This is why the pictures of my cars in my first picture were police cars, because it was supposed to be a joke. That the rate you measure scientific technical calculations of megaflops, billions of floating point operations per second. This is megacops, millions of car operations a second, but it spells cops. It's a pretty poor joke. So what we'll do now is we'll see how much faster on ARCHER2. There's a serial NumPy version. Okay, let's just do the S run again. This will be for the longer run. Now we need to, I'm varying the road size because if the job runs for only a few seconds, you don't get accurate timings. But we're looking at this, and for NumPy, we're getting 160 megacop. Okay, so that's quite good. Let's run that again. So already we're seeing the same picture, that NumPy for this simple program is 50 times faster than the naive Python, which is quite impressive, or disappointing depending on which way you look at it. You might be interested in how fast the C program is. Okay, I have a C version here. I have to basically update the make file. So this configuration is not particularly very good. The C code is exactly the same as the Python code. If we look at traffic, let's look at trafficlib.c. This is exactly the same code in C as you had in Python. That's how I wrote it. You know, the update loop is just the same. Okay, it really is just exactly the same stuff. Okay, written in C. The question is, how much faster is C than Python? Well, if we make, and I'll run it on the compute nodes. That seems a bit slow today, but if we run it on the compute nodes again, sorry, apologies, I've messed that up. We don't want to run Python. We just want to run the traffic model. We will see that we get about 260. So you can see that Python, naive Python is almost 100 times slower than naive C. But if you just put NumPy in, you're about less than half the speed. So that already shows you that if you want to do any numerical calculations, any array-based calculations whatsoever, you should be using NumPy. I've seen NumPy taught as a way of programming elegantly, which it is a way, but it also has these enormous performance benefits in Fortran, a couple of orders of magnitude. However, my statement to you is that I would make the code go 10,000 times faster. So we're looking for 30,000 megacops or 30 gigacops. So let's go to the PMPI. This is exactly the same code as we had on my laptop. It's just that when I run it on ARCHER2, let's run it on a single task just to check that it's well, no, it'll be very slow if I do that. So you'll have to take my word for it that the code is actually no. I will do the right thing. I have a script here now. I will cut the number of again out. Oh, sorry. This is Python. Apologies. This is NumPy. This runs at a reasonable speed. Apologies. I get myself confused. So let's just run this is the parallel Python program running on a single process, and we're just checking that there isn't a huge overhead. We saw that the raw NumPy was 160 megacops. Has introducing MPI slowed it down for a serial program? No, it's exactly the same, and we get the right answer as well. So that shows you that we haven't broken the program, but we actually want it to go faster. So let's just run it on 2. So it now prints out how many it's running on. Let's say running on 1 processes. Yeah. Let's run the Python program on 2 processes. And on my laptop, it only went about 50% faster. Here, we're hoping it will be a lot better than that. there is quite a large startup cost. A whole bunch of things. Python startup is quite slow, and the more processes you run, the slower it is, because you're running multiple Python interpreters here. So, and in the MPI model, so I said that you have the MPI library underneath, which is just a C library. How can that possibly support Python? Well, as far as MPI is concerned, you're running multiple Python interpreters. That's what you're doing. The MPI library sees you running multiple programs, all called Python. Okay, so that's what it sees. Python is just a C program that runs. This is taking an awfully long time, so I apologize for that. I don't. There have been some issues which I've noticed with job startup time is being very slow, and this is a lot slower than I had hoped for. It is running, it has been allocated resources, but it seems to not being. Well, I tested this just before lunch and it was all fine, so we maybe just be being a bit unlucky. Okay, there we go. And that ran at 270 as opposed to 160. So that's not particularly good. I actually think that there is, I think here that the road probably isn't long enough. We're not running for a long time. So I think not only is there a high startup cost of starting the program only does an internal timing. I think in Python, anyone knows more about Python than me, I think the first time you call things, there's often an overhead. It does kind of, it does on-demand stuff. And so I think that actually we need a longer road. Sorry, we need to run for longer. So what I will do, what we're looking is I will make the number of iterations 100 times bigger. But I will now run on 128 processes. So I'm going to run on a full Archer node, but we've increased the number of iterations just so it runs for a reasonable amount of time. If you run for much less than about 10 seconds, it seems to be dominated by startup costs. You need to run for a reasonable amount of time. But the figure we had was naive Python with 3 megacops on one process, and NumPy was 150. Now we're running on a single ARCHER2 node. We have to hope that we get something. So again, there's a number of there seems to be quite a slow top at the moment. I think maybe if the machine is very busy, slow, and it has a bit of a time of it. But also we are starting up 128 Python interpreters here, and each of those Python interpreters is importing NumPy and MPI for Pi, and it's all a bit of a. So there we go. We've got 23 gigacops. There we are. So that is almost 10,000 times faster than my naive Python. However, being an MPI program, I can just run on more nodes. So I can run on ARCHER2 on 2 nodes. I can run on 256 tasks. And this is right. So we're looking for 30,000 megacops to beat to hit the target of 10,000 times faster than a single naive Python code. I did propose the tutorial at RSECon with that title before I wrote the program. So originally the 10,000 times faster was an aspiration, but it was a reasonable guess. And I believe that if I run on 2 nodes, which is 512 processes on ARCHER2, we will achieve our aim of getting more than 30 gigacops once it starts up. Again, we may need to increase the runtime slightly to amortize. Again, on multiple nodes, the startup cost will be even higher. We're running twice as many Python processes, twice as many module imports, and we have the overhead of going over the network. But there we go. Yeah, we hit it. Yeah, so there we are. 37 gigacops, which is more than 10,000 times faster than my original program. So, I mean, that was really a bit of a, I mean, I went through a bit quicker than I expected, actually, apologies. The original tutorial was a whole morning and I had to obviously drastically cut it down. But I think what I will do is I will go back to the, I've lost my window. I will go back to the Jupyter window. And so this is our program which achieved this 10,000 times speed up on 512 on 256 processors. As I said, it was based on two really key things. One is the fact that the arrays are declared as NumPy arrays. So all our operations like initializing the road and calculating the number of moves and doing a copy back are done as single NumPy operations. Basically, you're just calling a C routine here. You're calling one C routine that goes away and does lots of stuff rather than doing something a million times. This is so where it's one. Yes, okay, so what this says, okay, so apologies, I wrote this so long I'd forgotten. So this is saying that you can read the syntax as replace the colons with a particular I. So this is saying new road of I is NP where new road of I, old road of I minus 1, old road of I plus 1. So this is updating the new road, the local version, based on the old road, the value of the old road, and the value down the way and the value up the way. And what this is saying is, if the old road value is 0, then it is set to the value of the one down the way. In other words, if there is a car down the way, it becomes 1. If there isn't, it becomes 0. If it's not 0, it's 1, it sets the value of the old road up the way. That means if the old road up the way is 0, the car moves and it becomes 0. If the old road up the way is 1, it stays the same. So it's a slightly contorted syntax, which I had to think about for a few minutes, but it allows me to express this loop here, okay, as this. So I should have gone back to this. So this is hard to express as a NumPy expression because it's a loop with explicit if and else in there. If you recognize, so you have a loop with an if and the else inside. That's not what you want. You want an if and an else with a loop inside, effectively. So basically, this is saying both these operations here can be expressed as array syntax, and this if could be implemented as a where, and then we can count these. So yeah, but so that's the first key observation. Replace your lists with NumPy arrays, and these array syntax operations for large enough arrays. Here the arrays were 10 million or whatever long. You get a speed up of order 50, and then to go beyond that, which is approaching the speed of naive C. To go beyond that, we need to parallelize the code to use multiple processes, and that is done through MPI. And if you're familiar with MPI, it's relatively straightforward. You just look up the man page, and as long as you use MPI, as long as you use NumPy arrays, then it is really relatively straightforward. And this, you can use scatter, which is a standard MPI operation. You can do sends and receives, and you can do global reductions here. And so, yeah, so those are the observations. So that was really rather more rapid than I had planned for, but hopefully it gave you a flavor of what's going on. The tutorial is still there. It may not work. There's instructions here. It may not work completely out the box because some of the instructions there were specific to the tutorial I ran on the day, but all the code is exactly the code the code I've been running now. And the only thing, so that was really all I had to say. I said I finished a bit earlier than I thought, but I'll stop sharing. So yes, I was about to go and look for the Wikipedia page. So thanks, Charlie. Give me a second. I've lost my chat window. I thought it was Rule 182. Yes. But there is actually a that's the equivalent thing there. Am I sharing that? Give me a second. So yes, I got it now. What I was looking for was Rule 184, not Rule 182. My aging memory failed me. So if I basically, if I share application screen, And so I have to talk to myself here. Rule 1H4. This is it. So quite astonishing that, you know, this stellar automaton is, it moves forward if it can, and if it can't, it doesn't. And there's a whole page on it if you're interested. Lots of stuff here. Anyway, so that's, but this was really just a motivation. But I would say, although it's a very simple model, I'll go back and hopefully, I did say this before, it is a surprisingly close analog for what a lot of parallel programs do. They update large arrays based on the values of the arrays and the neighboring values, and then a parallel program that requires a domain decomposition and halo swapping. Now, that domain decomposition and that halo swapping are particularly simple in a 1D stellar automaton, but conceptually they're the same as you would do for a large-scale parallel program. So I'm now happy to take questions, and please pick me up on anything I said wrong about Python. How do people profile this? So this is where my Python ignorance comes in. I don't know. There are classical HPC profilers. That was can have difficulty in seeing this double hop. You don't want to profile the Python binary. You want to profile the code which the Python binary is running. But Nathan, you're saying that map can unroll that. Map will give you Python line numbers. Well, that's useful to know. The other thing is you could use the built-in Python profilers. One of the standard tools called, I had an MSc student do this a couple of years ago, and I can't remember what it was called. But there's just at a reasonably broad brush level, the Python profilers will tell you how much time they're spending in different routines, including the NPI routines, because to the Python interpreter, the NPI routines are Python routines. And so what's it called? PyProf? Is it PyProf? Maybe not. Yes, PyProf. Yeah, cProfile. cProfile. Sorry, my student used cProfile, and that worked pretty well, at least at a first broad brush level. So the thing I did notice was that apologies, I'm messing over edges here. I did notice two things, well, three things. There's a delay to job startup that seems to come from Slurm at the moment. It's a small delay. Then there's quite a large delay to parallel Python startup, and I know why that is. That's because you're launching a large number of Python interpreters. Each interpreter will load modules. You import modules. That's a very big strain on the file system and such. Now, there are ways around that, but by default, that's what it does. But the third thing seems to be, as far as I can tell, the first time you call things in Python, they can be slow. And there seems to be some just-in-time compilation going on, so that you need to run for a long. So the first iteration can be slow, and then the subsequent ones can be much quicker. And so you need to run for, I always think, at least 10 or 20 seconds, otherwise. And I don't. Is that just-in-time compilation? I don't know if that will see if Python does that by default. I don't know if anyone can fill me in, but that was my what's the word? Rationalization of that. As I said, that tutorial is still there. I'll put the URL back in here just so you have it. Yeah, you get these. Yeah, you get these .pyc files, don't you? I'm never quite sure what they are. I really am showing my ignorance of Python here, but you get these .pyc files lying around. PyCache, sorry, the PyCache, isn't it? Yeah, which has these PyC files, yeah, which are, well, okay, yeah, I don't know what Py. Yes, so that, yes, that was in my slightly contorted terminology. It's what Dave was saying. There is some, it does produce some PyC file in some caching directory the first time you run it, and so that must be some overhead. Must be some overhead there. I think that was all I had to say. I got some notes here. The other thing I would say is that the MPI for Pi interface, although it works, is not particularly well documented or supported. My understanding is, correct, maybe someone may know more on this, that because there are so many Python programs using it now, that the MPI forum, who developed the MPI library, or specified at least, were considering taking on the Python support and specifying and maintaining that interface. But at the moment, it's a bit of a wing and a prayer. I personally found the documentation pretty weird. I just have to suck it and see sometimes. Never exactly clear what was going to happen when you did something, or exactly clear what the syntax was, because it is different from the MPI library. It's nicer, but for example, in the MPI library, being a C library, you have to specify everything. The question you always have in something like Python, what are the defaults? It was never quite clear to me what the default values were if you didn't specify them, and things like that. But I mean, I was quite surprised that basically that parallel Python program got within 50% of the equivalent C program. There's a parallel C program there as well you could run, but it's at that level of speed for an incredibly simple program and an incredibly simple programmer. But we got there in the end. Okay, so I don't have any more questions. I don't have any more questions. But I think I was very surprised by two things of this exercise. A, how close we got to raw C performance with NumPy, but B, how way away from raw C performance what naive Python was. So, okay, thanks everyone. So enjoy the rest of your day, and keep an eye out for, there will be more upcoming ARCHER2 seminars on a range of topics, which will be advertised by the same channels. Thanks everyone.